Of all the machines in the home, the television is probably the most mysterious. The very idea of a machine taking something out of the air and converting it to recognisable pictures would probably seem quite absurd if it hadn't actually already been invented. And all that's inside these machines is a mass of equally mysterious bits and pieces, none of which appear to do anything at all. There are basically two things inside a telly: the circuit boards that process the signal being picked up by the aerial, and the picture tube, or cathode ray tube, that actually creates the picture you're looking at now. We'll be looking at both in detail later on, but surprisingly, the idea of television started long before the days of electronics and cathode ray tubes. While an electric telegraph cable was being laid across the Atlantic in the 1870s, it was noticed that the resistance readings were varying according to the light falling on the instrument.
Quick, close the door. Now look at this. Look at that.
I say, the needle's moved.
Oh, how did that happen?
The reason was this resistor, made of an element called selenium. If we cover it up, you should be able to see the resistance change. Not very spectacular, but this chance observation out in the middle of the Atlantic was really the first tangible evidence that light could interact with electricity. This discovery, coming almost at the same time as Bell's discovery of the telephone, led to a rash of speculation that communicating in vision as well as sound would soon be possible. But no one could make it work. One of the reasons was the inadequacy of the selenium itself. It actually reacts quite slowly to a change in light, much too slowly to be any use for television. After the initial failures, more theoretical proposals for television appeared in the early 1900s, incorporating the newly invented cathode ray tube. But it wasn't until the 1920s, when powerful valve amplifiers and fast-reacting light-sensitive materials had been perfected, that the technology to make television possible had really arrived. A Russian physicist, Vladimir Zworykin, who had immigrated to America, patented an all-electronic system in 1923.
But I was keeping after my boss all the time for permission to work with television. So finally, after several years, I was giving the permission to do it. Now was the work I was looking for a long time. So I put all my efforts in this thing. I worked days and nights practically. And after about a year or so, assembled whole system, including the cathode ray pickup tube, which I called iconoscope, and cathode ray receiving tube, which I called kinescope, from Greek words.
Needing more money for research, Zworykin arranged to show his pictures to an executive from Westinghouse, where he was working.
He wasn't very impressed. So finally he asked me a few questions, mostly how long did I work with this system and so on, and departed, saying few words to the director of the laboratory. Later on I found out that what he said was, put his guy to work on something more useful.
So Zworykin's system was delayed, which left the field open for a young Scottish inventor. John Logie Baird was one of the least academic early experimenters. In his youth, he worked as a mechanic while also embarking on entrepreneurial schemes.
Johnny, I was wondering about the undersocks. Do you have any on the go at the moment?
The undersocks. That's a wee sideline of mine.
He also attempted to make artificial diamonds using the facilities of the power station where he worked.
This will make me famous. To create diamonds.
Dogged by ill health, he then moved to a warmer climate, Trinidad. Here he made attempts to start up a jam-making factory, but was defeated by the local bees.
Now, I think everything's ready, isn't it?
I've got the high voltage.
Cecil, just...
Back in Britain, he then started his experiments for seeing with wireless, attracting a group of enthusiastic amateurs around him. By 1924, he had a crude mechanical system transmitting silhouettes.
There
it is!
Oh, super!
His main contribution to the history of television was really his flair for publicity, exciting the public's imagination. He also gave sets to very important people.
Good morning, Mr. Baird. Just one there. Thank you, thank you. All right,
Miss-
sir, can
Mr.
you hold it up
MacDonald,
for us?
here's
Very
your
good.
televisor.
And again, sir. Won't take you long, sir. Right, thank you very much.
Finally, in 1936, the BBC arranged trials of Baird's television.
Oh, good morning, Mr. Baird. We are the BBC,
Thank
of
you,
course.
thank
We will
you,
be with
thank
you
you.
any moment.
In competition was EMI's all-electronic system similar to Zworykin's. Baird's cameras were cumbersome and immovable.
You're moving too much.
In contrast, the EMI cameras were compact and completely portable. So Baird lost the competition. But undeterred, he continued improving his system and in 1946 showed a giant colour picture.
Oh, marvellous, marvellous.
But a week later he died, aged 58. Since then, all television has been based on the EMI electronic system.
This is direct television from the studios at Alexander Palace. And now you're going to see and hear someone you know well. A mighty maze of mystic magic rays is all about us in the blue. And in sight and sound they trace living pictures out of space to bring a new wonder to you. There's joy in store, the world is at your door. It's here for everyone to view. Conjured up in sound and sight by the magic rays of light that bring television to you.
The heart of any telly is the picture tube itself. If you look inside, you can see there isn't much inside really. In fact, there's nothing at all. It's normally a vacuum when it's working. We usually think of electricity flowing in wires, but under the vacuum inside the tube, the electricity is actually flowing from the neck to the screen as a sort of invisible beam, a stream of electrons. The inside of the screen is coated with chemicals called phosphors. And it's actually these phosphors that you're watching at this moment glowing behind your screen. The television tube needs a high voltage between the neck and the screen to make the electrons flow. You can see this wire going to the screen does look rather like the spark plug lead of a car, which also carries a high voltage. The device that creates the high voltage in television does have other uses.
I made this plasma lamp entirely out of old television components. The main components being the line output transformer and transistors which supply the television with a high voltage. It's quite a fun thing. They're sold in some of the large department stores for an amazing amount of money, approaching £2,000, some of the bigger ones. This one was a total cost of about, I suppose, £7 or £8.
This is the National Museum of Film Photography and Television in Bradford, and this part's all about how television works. I helped design it with the curators a few years ago. In this first display, you can see the spot of light caused by the electrons hitting the phosphors on the back of the screen. If I hold a magnet over the screen, the spot moves because the beam of electrons is attracted by magnetism. And with an electromagnet strapped around the neck of the tube, the magnetic field can be very accurately controlled so that the spot can be moved precisely anywhere on the screen. And of course, if I move the spot into this patch where we scrape the phosphors off, the spot will disappear. Also, by adjusting the intensity of the electron beam, the brightness of the spot can be varied. In a television, the spot is made to scan the screen line by line. The image is formed by varying the intensity of the spot as it scans. This model uses ink marks on string to represent the variations in intensity of the scanning spot, so you can see how the picture builds up. So if we increase the scanning speed, the illusion of a complete picture starts to appear. The sharpness of the picture depends on the number of lines. Today's sets have 625. The original EMI system had 405, and Baird's had only 240. Gerald Wells, who runs the West Dulwich Radio Museum, has collected some of the first domestic television sets. His earliest set doesn't look like a television at all.
It was a Model 900. It was probably the first television in the country of its type, and it was bought out in time for television. Originally it was dual standard, had a switch for 240 line and 405 line, so you could watch with Marconi EMI system or the Baird system.
It doesn't look like a television.
No, it doesn't, because in those days the early cathode ray tubes were so long in the neck, the only way you could mount them was vertically, with a mirror in the lid. I mean, reverse the scanning coil, so the picture was the right way around, and you actually watched it in a mirror. You could watch it either in that position for sitting position, or you could turn it up like that and watch it in the standing position. Or you could close it down altogether, and it just looked quite an inoffensive sort of cabinet. As nobody could afford that model £100 ago, Marconi EMI bought out the 707 and 705, which was a 5-inch and 7-inch set respectively, which would sell for 29 guineas and 31 guineas. They maintained that even if a television system failed, and they had a sort of an idea that it might be shut down somehow or other, but at least you had a good quality radio for your money. They then started getting the screens larger again. They started off with large screens at 12-inch, then went down to 5 and 7, and then gradually they crept up to 9-inch. With this model, the 709, which was quite a fine receiver. This one's working a bit, and also a first-class radio. This came out at about £60 and was currently in the shops up till the outbreak of war.
Which is the earliest example of a post-war set?
Well, I'd say it was this 9-inch Pi here. Pies didn't do anything astounding before the war with television. They made a few, but weren't particularly brilliant. And then after the war, with the experience they'd gained from radar and the money they'd made out of the war, they'd ploughed back into their company. They produced this thing. It was an absolute work of art.
It looks much more compact.
It's very compact, beautifully designed, easy to work, had a little panel on the front where you could get at the line hold and frame hold controls to adjust it. It gave a high-definition picture, mirror-backed tube, and all the technology we'd learned during the war came out in this. It was brilliant.
And this portable here, what
well, this looks certainly portable. It's the little 9-inch Bush that came out in 1950. A lovely little bit of engineering, also slightly out of adjustment, and they made use of a jelly mould with the Bakelite. It was a lovely substance. It matched their DAC-90 radio they bought out at the same time. It was small, it was compact, it didn't have a large mains transformer in it. It was miniature valves and modern plastics again. This was a lot safer. You couldn't kill yourself on one of these. Well, you could if you were absolutely stupid. But these sets were absolutely lethal. In fact, before the war, our main insulating materials, of course, was paper, tar, wax and varnish. The first man to be killed by television was a friend of mine, and that happened up at Newton New Willows in the 50s. On a set I'd actually taken up there, one of that model. So it was brought home to me very definitely how dangerous these sets were.
So this
there was no second chance of it.
So this was a big improvement.
One touch of that and you're in the service department in the sky. You've had it. But these, if you did catch hold of a high voltage, the resistance of the skin and the moisture in the body would collapse the voltage. So apart from a very nasty burn, sometimes you weren't even really aware that you'd burnt yourself until you come to wash your hands in Ajax, and then you'd know all about it. But you certainly didn't kill.
The pictures on these old televisions now have to be converted from today's 625 lines to the old 405 line standard. This converter is a bulky machine, and Gerald's now got such a large collection of televisions and radios that the only place he could find for it was next to his bed. Colour television uses 3 different coloured phosphors, red, green and blue, with a fine metal mesh behind. This mesh has a grid-like pattern of tiny holes or lozenge shapes. This is a mesh we've taken out of a telly, and if I hold a torch behind it, you can see the holes clearly. Inside the tube there are 3 electron guns and 3 separate streams of electrons. The mesh or mask blocks the electrons and only lets them through the holes. So each beam hits the screen in slightly different places. Inside the screen, the 3 coloured phosphors are laid in fine strips, here shown greatly enlarged. When the mask is in place, each electron gun, here shown by holes in white card, only reaches 1 colour of phosphor. Now look closely at an actual television. You can see the grid-like pattern over the whole screen created by the mesh. And if you look even closer through a magnifying glass, you can see the 3 coloured phosphors. As the picture changes, you can see that any colour can be created by just varying the relative intensity of the 3 phosphors. Even white is obtained by mixing the 3.
We made this wind-powered clock for the Liverpool Garden Festival a couple of years ago. The wind-powered generator on top merely charges this battery. The battery powers the electronics, and the electronics supplies an impulse to this windscreen wiper motor, which actually drives the clock movement round every 30 seconds. Now, when I developed that clock unit, I did the electronics indoors in the workshop, and it worked perfectly, and I left it on test for about a fortnight. I brought it out here, installed it in the clock, had second thoughts that I'd connected it wrong, so I reconnected it, and this time I connected it backwards and blew the whole lot up, every transistor and every chip, and had to start from square one again. And as a friend said, it's easy to make something which is foolproof, but it's very difficult to make it idiot-proof. You can soon connect something backwards, and you can't see you've done anything wrong. You know, but when you actually go to connect it up, you get a big bang, a puff of smoke, and all your work is gone. You've wasted a fortnight.
I think it's because the electronic components don't move or give any indication of what they're there for that it's so easy to make mistakes like Rex's. The electronics in a television, which process the broadcast signal and power the loudspeaker and tube itself, are very complicated. But they're not quite as baffling as they first appear. One thing that makes electronics less intimidating to me is that all the circuits are made up of a relatively small number of different types of component. I can show you quite a lot of these just with a light bulb and a battery. A resistor just acts as a restriction and makes the light dimmer. So twice the resistance makes it dimmer still. A diode lets the electricity flow one way, but not the other. A capacitor stores electricity, only letting the current flow until it is fully charged. It can then release its stored electricity again when connected straight to the bulb. A transistor often acts as a sort of switch. The tiny amount of electricity from a battery made of a potato can switch the main battery and power the headlight. In fact, over 90% of the components on this board are like the ones I've just shown you. The integrated circuits are just a lot of components all sandwiched together, mostly transistors. I do admit that when you start joining everything together, the circuits very quickly become very complicated. The other thing that helps to reduce my intimidation about electronics is that you often don't need precise knowledge of a circuit to mend a fault.
When a repairman repairs your telly, some of the faults are blatantly obvious as soon as he takes the back off. Components are either burnt out or been smoking, and you can actually smell the pungent smell from some of the components actually burning. Other faults are fairly obvious, like dry joints on the solder. That's when the solder hasn't flowed properly onto the component, on the circuit boards. Although the circuit looks really complicated, it can be rather likened to a road map of the British Isles. And if you were travelling between London and Brighton, for instance, you're not really worried about what the roads are doing around Glasgow and Edinburgh, and the same really applies to a TV set. Like reading a map, you can soon find the area you're interested in without detailed knowledge of the circuit boards. You can then narrow the fault down to a few suspect components.
We've managed to get a picture out of most of these old scrap tellies. From the outside, they don't look very different from modern tellies, but inside, things have changed quite radically in the last 15 years. For a start, the old televisions needed an elaborate set of adjustments. There were so many knobs that they were rarely set up accurately. Most of these adjustments have now become obsolete simply by ingenious refinement of the tube design. The older sets also used much more power and generated much more heat, and heat isn't very good for electronics. Finally, instead of the individual valves and transistors, modern sets use integrated circuits. A modern set has less than half the number of components of a 15-year-old one. It looks as if there's almost nothing inside in comparison. All this has made tellies much cheaper and simpler to build, and it's also made them more reliable. I think they're the only machine in this series that's actually become more reliable in recent years. I think it's quite wonderful that something that so recently was stretching the limits of modern technology can now be achieved so easily. The days when people rented their tellies because they were so expensive and they needed mending so often are really gone forever. And all these old elaborate tellies, none of which are working properly anyway, are not really worth mending. But instead of just throwing them away, we decided to give them a rather more dramatic end, particularly as it's the end of the series.